thanks so much for the intro, and thrilled to be here. Okay, so this is the my clicker. I want to share some kind of directions on the autonomy at scale, at least what it means to me. So let me start with a question. How many of you have a relative or a friend, or perhaps that's even you, that struggles with everyday, thank you, that struggles with everyday tasks that most of us take for granted? 15% of world population, or 1 billion of people, live every day with some sort of disability. And autonomous agents, whether that's in all shapes or forms, whether that's self-driving cars, right, service robots, or digital assistants, have tremendous opportunity to make difference in so many lives, right? So what do we need for that opportunity? It's an important problem, right? We need robots and systems to work in real world. And real world is messy. This is just an example of robot where we ask it to go from one point to the sink several times, and we just let the camera roll. And people are there. Now this thing is blocked, so it needs to go and figure out what it should do and adapt and so on. This is reinforcement learning policy running. Trained fully in simulation, and then just plopped on the robot. It takes the LiDAR observations and outputs the velocity, linear and angular, and I'll talk a bit more about that. But this is the real world. There is a custodian. We did not script that, right? So we need to be able to train the agents to be able to do that. So the big question, I think, when I think of what wakes me up in the morning and keeps me going, is the core of the research question is how to effectively train the agents, then bring joy to the users, right? And now Joy is doing a lot of work here and encompasses all the messy stuff around generalization, safety, preference, user trust, right? That we know, and there's tons of work in that space, and it's probably even more that we don't know, right? And then there is the effectively. And today I just want to focus on the effective part, because let's ask what is one thing that keeps us from being able to scale this up and train more agents to do more tasks and so on. So from that perspective, let's see how we're training the RL agents, right? It's a very engineer in the loop problem. You have this messy world that we just saw, and then we shove it down into POM MDP tuple. And what does that mean is that we have a poor engineer there that is starting and says, okay, what are my awards, right? What is my environment that I should be training? Which algorithm? And he goes, you try and see how it works, and comes back and observes, and we try something else. And as we saw earlier today, this is reinforcement learning problem. It's a sequential decision problem. And if it is a sequential decision problem, then, oops, let's learn it, right? So for today, I want to touch on these three pieces: rewards, algorithms, and environments and tasks, how we can automate the learning process and remove the engineer in the loop. So for the first part, rewards, because this is one of the first things that we encounter training. Let's look at the example of this mobile robot that I just showed in the unknown environment, right? We want to train a goal condition policy that goes and deals with whatever I'm given where I need to be, and then just need to deal whatever is in my way. So for that case, my observations are LiDAR observations. I mentioned what the speed is, and then we train in very simple simulation environment, 20 by 20 meters, straight walls, and so on. What's the reward? The reward is, in this case, your objective. You reached your goal, you didn't, right? However, that's not going to train. We do have a good intuition over what these features of the reward are. Distance to the goal, my angle, my speed, distance to the nearest goal, and so on. But how they fit in together, we don't know. So we call this intrinsic reward. This is some kind of parameterized mess of the reward that we want to learn. So we do that by basically training a population and agent, each one of them instantiated with a different reward, evaluated then against our task objective. And this task objective can be stuff that's current inverse learned reward or whatnot, right? Is the thing that you really want to optimize for. And then we observed, and then we have the mutator that proposes the new reward, and we do that loop for about 1,000 times. And we have the policy. That policy then we are able, so here is an example of the simulation environment. It's very simple, just a kinetic model. There are no moving obstacles, no nothing, right? And you plop it on the robot, and it kind of transfers to real world. And not only this methodology works for mobile robots, it also works with the systems with the kinodynamical constraints, which kind of ends up being approximate solution to the two-point boundary problem that wasn't available before. So we can actually start controlling more difficult agents as well. So in this space then the question was, okay, this is super promising and exciting. Is this kind of robot navigation thing, or is it more general? So benchmarking across different environments and different algorithms, we find that the more difficult task it is, the more bang for the buck there is. So orange line here is reward learning. Blue line is hyperparameter tuning with the same methods. And then the green one is your baselines on a humanoid. On an ant, not much difference. So then the second question is, okay, if I have fixed budget, should I use that for the hyperparameters, or should I use it for the reward search? And again, the more complex task is, the more likely you're going to start getting policies that are with the reward tuning. And final kind of question that we ask here that kind of ended up a surprise factor is that there is a codependency between the rewards, these intrinsic rewards parameters, and the algorithms that we use. So if we take Mujako, if you know the reward in there, they're like fixed parameters. If we let learn, we train towards that objective, but we re-parameterize it and learn reparameterization. Depending on which RL algorithm we use, different parameterization does that. And that was surprising. Okay, so TLDR here, intrinsic reward is your friend if you have snarly problem and you can afford it. Now, next I want to talk about the RL algorithms. The new RL algorithms seems like they're popping out like mushrooms after rain. Nowadays, there's lots of them coming out, and the question is why, right? And if that's the case, again, can we automate that process? So one insight that we have here is that reinforcement learning loss functions are really computational graph, that we can add one or two things, right, and so on. And if that's the case, can we then involve the graph and actually have something interpretable, because it is a math function that all we know how to deal with, and kind of see where that gets us. So that's what we do using basically the similar methods. We train population of agents. In this case, we have a hurdle environment, which is the cart pole. If it can't pass the hurdle environment, there's no point going further. And then kind of have a couple of simple maze environments for training. We use regularized evolution to mutate the graph and the population. And we also use a hashing function to kind of reduce the complexity and be able to kind of cope with the fast and kind of repeat the loop. And then we evaluate on previously not seen environments, even including Atari games. It takes about 20 to 50,000 different graphs to go through. One of the algorithms that we find is we're calling it DQN regularization. And what's very interesting about it is, Sergey was talking about conservative, QL earlier. This guy also has the regularized parameter. It looks very much like these offline RL that kind of cuts off, which was very interesting. And then if you see how well it performs, it's the blue line over there compared to the DQN, even CQL. It outperforms them in the unseen environments. Even in Atari games, the numbers here are taken out of the published papers, and then DQN reg has its own. The outperforms them in all 4 games that we tried. So that's exciting. What's also interesting is, What's also interesting is that this algorithm is consistently discovered across different seeds, top performers are kind of their equivalent up to a constant. What's exciting is that this is the first time that we have large number of reinforcement learning algorithms and their behavior, or how well they're performing, as a database for further study. There are math formulas. We can use the same tools that we know and love. They can serve as an inspiration for theoreticians, right, to go and analyze which pieces of the reward they are doing, which are there or not. And it's just kind of one example here, that insight that we got is if we take these 20,000 algorithms and we put a histogram on them, we see that they kind of map to about 200 different performance values, which is surprising, right? That means that there is a huge classes of the graphs, computational loss functions, that are functionally equivalent. What does that mean and what's the implication there? And yeah, data is there. If anybody wants to go dig in, please. And then last, okay, I'm good with time. Last piece that I want to talk about is how to do, again, we're talking about scale. We want to do not one task at a time, right? We want to do many tasks and so on. So let's go in, step into the autonomous web navigation, or what we call compositional tasks. The idea here is that we have a single agent that can solve many different compositional tasks. And compositional task means that you have some primitive behaviors, manipulation tasks, and you can kind of string them into ever more so complex. Maybe in cooking, like if you can chop and stir, you can make many dishes by kind of combining these behaviors in different. In a context of web navigation, say you want to do one-click checkout, you want to change a password or order food, you're always entering your name, your address, right, and so on, and you hit OK button, the new room shows up, and you kind of need to go through a set of pages. There is lots of noise around it, there are ads, environment change, and so on. We don't need generally no additional training, so can we have agents do that for us? Can we have one generic agent that does that? Now, current state of the art, in these environments, we can't do training on the websites. We can't buy millions of iPhones or so on. And the size of the websites is about, commercial websites is, I don't know, 30,000 DOM elements per page. The prior existing benchmark has 100 DOM elements. So there is a huge difference there between the available benchmarks and the real world need. And the existing methods require millions of interactions with a single environment and only trained on a single environment. So there is like a huge opportunity there that we can go. So to address this, first we created a generative mini-web environment, which is generative environment and a benchmark for compositional tasks, and includes this web navigation space, mazes, and mining environment as well. And the idea is that we start with, you can feed your generative environment with set of primitives, and then it combines them into up to, I don't know, 5 to 7 different pages with, I don't know, up to 15, 20 elements per page. Then you can add different pictures and so on. And we can create and kind of generate these websites. And there is the benchmark with it. And then to train the agent, we can't do a zero shot. Manual curriculum does not work. We tried that. So we ended up with having 2 agents, having teacher agent that generates the environment or the website of just the right challenge. And here you can see it kind of rolling out a website for population of reinforcement learning agents to train from. And then they train, we observe how well they're performing, and the LSTM gets back the feedback, the regret, which is basically the range of between the performance of the weakest and the strongest agent, and the best performing agent. And that these 2 signals are then used for 2-part loss. The loss that controls how well The piece of information, the reward that gets how well the best performing agent is used, it's used to control the budget or how difficult the environment is, how many elements we're putting in. So if the best agent is not doing well, we're going to the LS team is going to reduce the difficulty and just have like one or two elements and so on. If it starts going well, it's going to continue. And then the range gives us how interesting this is. If they're all performing the same, then we should kind of include more variety and kind of sample more elements from it and so on. And then we evaluate these agents on not seen before websites. So what are some conclusions? Not surprisingly, we see that early on during the training, the websites are simple. Later on in the training, they're more complex. And mind you, these are not semantically correct websites. You can have the first name 15 times, it doesn't care. In terms of performance, the blue line is our method, the red line is manual curriculum, and the green line is peer method without the budgeting. We see that it really generalizes to the new environment, the curriculum piece. Interesting part about this curriculum is that it does not take this, it doesn't care it's RL agent, right? The only thing it observes is how they're doing. It can be human, it can be imitation learning, behavior cloning, you name it, right? The interface is very clean. And then we also see that over the duration of the training, it kind of shifts the distribution of the primitives that puts on these websites towards those that are important for the task, from ads to really like, okay, let's get the stuff that's going to get the task done. And then finally, the question is, does this really work? And is the benchmark good enough? And is the methodology good enough? So we scraped from the web 3,500 primitives, which then induces the generalizable task space to 10 to the power 31. We train the agent. These are mostly kind of login primitives in this case, and evaluating the benchmarks, and numbers suggest it does not solve the benchmarks, they're out of distribution, which means that benchmark is difficult enough and kind of holds water. At the same time, now remember, we did not do interactions, we just scraped the DOM elements, created the website, trained the agent. Now let's try to have it go and interact with these websites, so they're now they're in distribution, and we're getting 93%, which is very exciting. All right, so I know I'm running out of time, I'm finishing. We saw 3 examples here on learning the rewards and learning algorithms. In this case, these are the system properties of the agent, right? You've set them, and for the duration of the training, they stay the same. You can kind of say that this is nature of the agent. On the other hand, for the environments and multitasking, web navigation, the curriculum, the only thing that was changed between this and the prior work is what are the websites and the environments that it was trained on. And that improves the generalization. This is the nurture, right, of the agent, how we kind of trained it and so on. And that raises really the question of what is the fundamental role of nature versus nature in these agents. These are very complex systems, right? This is very simplified. We're learning rewards, neural network architectures, policies for what we're sampling out of the replay buffers when and how we're doing when we're running the updates, how many updates. It is a very complex system that we're just kind of scraping the surface, the interconnectivity of it. So I think it would be, Danny made this point, and understanding what are the theoretical principles and how we can automate that learning would really go a long way in the future of the agents. And with that, I'd like to thank you and thank my collaborators.